Hi, I'm Beverly Owens, Lab Section M03 with Lab 9, Motion of a Spring. The problem we are addressing is understanding and predicting the motion of our spring and making changes to the code to plot the predicted and the measured positions as a function of time. We are determining the period of oscillation in the y and x direction and calculating the corresponding changes in the spring potential energy. Our main result from analyzing our spring Earth mass system, we found the predicted position and measured position in the y direction to be negative 0.63 and negative 0.642 meters, and for the x direction negative 0.045 and negative 0.066 meters. We determined the period of oscillation in the y direction to be 0.79 and in the x direction 1.63. We calculated the change in the spring potential energy to be 0.0023 joules using our video analysis, the momentum principle, which is Newton's second law, and the energy principle, which is the first law of thermodynamics. In Tracker, the stretch length of the spring was 0.7 meters with the calibration stick. The origin is at the spring attachment with the positive y direction pointing up and the positive x direction pointing to the right. The position of the mass, 0.402 grams, was plotted over 49 frames, giving a video length of about 4.7 seconds with a frame rate of 10.53 frames per second. Looking at the model in VPython, the initial conditions were a mass of 0.402 grams, an initial position at negative 0.105 meters in the x direction, and negative 0.606 meters in the y direction. This was found from Tracker. And there was also a velocity of 0 because the video begins when the spring is stationary, when time is 0. The spring constant was 6.87 and the relaxed length of the spring was 0.127. This was calculated in a previous lab by first determining omega to find the frequency, which allowed for the calculation of the spring constant and L naught. The gravitational potential energy and kinetic energy were also calculated to later solve for the energy and work of the system. When time is less than 4.653 seconds, we could model the oscillating spring using the net force, which is the force of gravity plus the spring force, which was found from the spring constant, stretch, change in stretch, and L hat. This allowed for the spring force, position, and velocity of the mass to be calculated. To find the energy changes, including the spring in our system, we have our energy equation so that delta T is equal to delta kinetic energy plus delta gravitational potential energy minus the work. To find the spring potential energy, this is equal to 1/2 Ks times stretch squared. And the change in the spring potential energy is found by subtracting the initial spring potential energy from the new spring potential energy. When the code ran, delta US was equal to 0.0023 joules. The computational model successfully predicts the spring during the time of about 4.7 seconds in both the x and y directions. You can see from the graphs that the red representing the computational model and the green line representing the real-life model, that the models align very well, and that the ball versus ball 2, which ball 2 is our real-life model, have very similar positions in both the y and x directions. So what does it all mean? When we're comparing the periods of oscillations, the x component of the period of oscillation was 1.63 and the y component was 0.79. This was calculated by taking the average between the two peaks of the graphs. The oscillation periods differ because the spring was stretched more in the x direction when Dr. Greco pulled the spring, causing the period of oscillation in the x direction to be larger. When we are looking at the work of the surroundings, I found that the work done by the surroundings is 0 because the work done by the system is also 0. This is due to everything being analyzed is in the system, the spring, earth, and mass. This satisfies the energy principle because energy is conserved. For our third question, when we define the gravitational potential energy and we're changing the origin, there's no change of the physics, only the origin changes, changing the height. Physics can't depend on the physical system, so we can change the origin, and as long as everything else is changed equally, it doesn't really matter. We can see this in our graph when we change the origin of the predicted ball, represented by the red line. The predicted model still shows the same trend, just the orientation is changed. So the red line just moves up and instead of staying where the real life model is, represented by the green line.